Hi, I'm Samuel Nnqvist from Turku NLP Group, and I'm presenting the paper Multilingual and Zero Shot is closing in on monolingual web register classification. I'm going to first talk about what web registers are, and then I'm going to look at how to classify these both monolingually and cross-lingually, which is the special focus on this paper, where we do it training on multiple languages. So first of all, registers, or in particular web registers, are different genres or situational dependent variation in language use. So different ways we write on the web depending on situation and purpose. And these registers define categories, which are important predictors of linguistic variation. And we're interested in being able to recognize these and classify them. Um, for example, when we work with web crawl data as a way to create metadata about what kind of um, text we have, which is important if you want to use this as a corpora, uh, and compared to if you collect corpora from selected sources such as news, then you know what you have, but from the web, it could be anything. So it's important to be able to recognize register. So register could be okay. So I think the types of text, like we see Wikipedia articles, it's encyclopedic um, variation of language, or we have novels, or here's an example of a schoolwork, which is another very different way of using language, or a recipe, for example. So when we talk specifically about the web registers, we have a wide range, such as narrative, opinion, discussion, instructions, persuasion, etc. So these define top level or main level registers, and then we also have more specific ones like part of narrative. We have news article, or part of opinion. We have opinion blog, for example. And typically, a web page can mix multiple of these as well. So news and opinion can be mixed, or um, news sites often have comment sections, so that's the discussion being mixed in and so on. And for example, persuasion is sometimes mixed with information uh, or news even. So this, for English, there's a corpus called Corpus of Online Registers of English, or CORE, which is a big corpus that have been collected through different search queries. So this represents the open searchable web, and it consists of nearly 50,000 documents, which have been manually annotated for register using a two-level taxonomy with 8 main registers and 27 sub-registers. And the way this corpus has been built, it's an empirical approach to seeing what's really on the web, what types of language use, as opposed to many previous works that specifically select certain types of register and then go out and collect data for that register. So this is, in that sense, more empirical approach to collecting web data and the registers that are actually occurring on the web. So for us, Core is a very extensive and a useful resource for training classifiers that are able to detect register in English. And we also have some similar corpora for other languages. So Since 2019, we have FinCore, and since this year, we have the Swedish and the French cores as well. So core corpora. Each of these consisting of about 2,000 documents, so they are relatively small in comparison to the English one. But it's a good starting point for evaluation and for training some models for these languages as well. Um, the question is really, can we train models specifically for these languages? They can go beyond English and classification in English into these languages and maybe beyond. So in previous work by Repo et al., they look at classification both monolingually and cross-lingually from English in order to go beyond English web register identification. So monolingually, they model Finnish, French, and Swedish based on the available data, which, as I mentioned, are only a fraction of the size of the English one. So 3 to 4, 35% of the size of the training set. But still, with the XLMR transformer-based language model, as well as some multilingual bird models, they're able to achieve strong results in these languages, so between 73 and 83% F-score. And in zero-shot experiments, they get good cross-lingual performance as well, training on English and testing in Finnish, French, and Swedish. So the previous baseline in that setting is with a CNN model, about 40 to 47%, and they get a strong increase over this at 61 to 69, but there's still quite a gap to the level we see for monolingual modeling. But they also explore how many training samples you need in the different languages in order to be able to beat zero-shot performance. And it turns out it's as little as 150 to 400 examples that are needed. So this shows that it's kind of lightweight or small scale annotation in a target language might be a quite worthwhile effort in order to get good performance using these modern language models. So the question in the current paper is how can we improve about these results using multilingual training, both monolingually and cross-lingually. So on the one hand, we want to train on all languages and predict on each and evaluate on each of 4 languages separately. So kind of predicting in language or on the languages that we used in training as well, and compare these numbers against monolingual training results from previous work. And secondly, we want to do zero-shot cross-lingual prediction training on 3 languages at a time, leaving out the one being tested on, and see if we can improve above the results that we saw before when the models were trained only on the extensive English data. So we see that we use a sampling and training strategy that picks one language with uniform probability, and then to create one training batch. So this results in looping over the small languages more often, and we hope to see the English data at least once. So we train for longer with early stopping and lower learning rate. So in order to achieve this, so the learning rate is about 1 order of magnitude lower than previous um, in previous work found to be the best. And then we first look at the monolingual results and comparing against the monolingual results. So in the previous work, on all languages, the average was 77.21 F score, and we're getting um, on par result here with the multilingual training. Um, so that's when we include all languages. But if we look at, if we exclude English and look at Finnish, French, and Swedish, we get a noticeable increase. And if you look at the breakdown here per language, you can see that especially for Finnish, the blue one, there's a big increase and a bit of increase for French and Swedish as well. But looking at the measured or estimated interannotative agreement, which are these horizontal lines that we have for French and Swedish, we see that there's actually not much room for improvement to be had, even though these interannotative agreement levels represent a lower bound of agreement. So it's a bit of a soft theoretical upper bound for modeling. If we also train a so-called master model, which is one model that we train once and hope to be able to apply successfully to all languages, whereas the other results, previous results, were optimized individual for each language to kind of pinpoint the optimal performance possible. But we see that for the combined master model, results are very similar, so just slightly lower for all. And also here, for excluding English, we have 78.74 compared to 78.82. So, and also here we see visually that it's pretty similar. French even improves, whereas Swedish decreases a bit in the master model. But all in all, the results are on par. Then we see in the zero-shot experiments, in previous work training on English, the results were on average across languages 64.95, and now when we train multilingually on the all but one setting, we get a huge increase up to 73.98. So thinking in terms of gap between zero-shot and monolingual models, in previous work, this gap was 13.87 F score, and now we're down to 4.84. So this is represented here. This is the gap in previous work. The arrows represent how much, it represents the distance to get up to the monolingual performance. And here we see that for Finnish, French, and Swedish, it's much smaller. So it's more than half of the gap, or 65% of the gap has been eliminated. So we're a good, I've traveled a good distance on the way to the performance levels we see for monolingual models, but there's still some improvements to be had. So in conclusion, we see that in monolingual training, we're able to improve performance on the three smaller languages we have, while performance in English is hurt. But even on average, including English, performance is on par. And especially interesting looking at the zero-shot performance, we see this great improvement when we do multilingual training, and the gap more than halved to a level of about 5% F score. And in future work, we would like to look more into cross-lingual performance into other languages, especially more distant languages, in terms of language family and culturally. And we would like to explore in detail more why different registers and how well they are uh, transferred cross-lingually, also looking at specific classes, specific register classes. So thank you for your attention, and I'm looking forward to your questions.